Hey guys, let's go ahead and get started with the bell ringer. I want you to factor these polynomials. You can factor the first one by the way we started factoring or use the AC method, and the second one you should use the AC method. So go ahead, work on these two problems. When you're done, go ahead and I'll play the video and get your answers. So go ahead and pause now and get to work. So these are your solutions. The first one is m minus 8 times the quantity m plus 10. The second solution is x plus 2 times the quantity 2x plus 5. So let's go ahead and find the product of these two binomials, x plus 5 times x minus 5. I'm going to use double distribution, but you can use the box. So first we'll do x times x, giving us x squared. Then we'll do x times negative 5, giving us negative 5x. Then we'll move on to the 5 times x plus 5x, and 5 times negative 5, which is negative 25. And then when we simplify this, it becomes x squared minus 25. So what happened to the middle term? Meaning, what happened to the term with just an x? And everything we've worked with so far, there's been something in the middle. Well, what happened to the middle term in this one is it canceled out. So it canceled out. And what do we notice about the first term and the last term? Well, if I look at the first term, it's x squared. Of course, that is a perfect square. But if I look at the 25, the negative 25, that is also a perfect square. So both terms are perfect squares. Both terms are perfect squares. So looking at where this came from, what can we say about the factorization of a polynomial? It looks like this. So if we're looking at it came from x plus 5, x minus 5, and we got an x squared minus 25, I can tell that my first terms in my parentheses is going to be the square root of the first term, and the square root of x is x. So these first two terms are going to be x and x. And since that we have a negative here, I know one's positive, one's negative. And then I want to look at the last term, 25. It's going to be the square root of that as well. So 5 and 5. Also, if I think about, I need to find the factors of this negative 25 that add up to 0. Well, that's plus 5 and negative 5. And what we have here, ladies and gentlemen, this x squared minus 25 is what we call a difference of squares. A difference of squares. So if we have a polynomial that looks like this, it takes the form of a squared minus b squared, we call it a difference of squares. It's going to factor into, of course, two binomials. Square root of the first term in the first box, so a and a. Since it's a minus in the middle, we know our signs need to be opposite of each other, so plus minus. And then the square root of the second term, and b and a b. So if we're looking at the example, t squared minus 64. If I follow that pattern of a squared minus b squared is going to factor into a plus b times a minus b, I know it's going to be two binomials. I know I'm going to have a t here and a t here. Since because of that negative, I'm going to have a plus and a minus. And then the square root of the last term, the 64, so plus 8 minus 8. Or if you don't remember that pattern, it's still okay to factor the other way. Just looking at the factors of negative 64 that add up to 0. So the factors of negative 64 that add up to 0, well, those are 8 and negative 8, giving us 0. So it's going to be t plus 8. And again, t minus 8. So either way works. So again, if we don't recognize this, I guess this goes down here. We can still factor in it normally. So you have another example here. So this time 16a squared minus 9a squared. We haven't really seen anything like this where we have a squared term last as well. That's where this difference of squares really comes in handy. If you notice, 16 is a perfect square. 9 is a perfect square. That means I have a difference of squares. So it's going to break up into two binomials. First term being the square root of this term, square root of 16h squared is, well, square root of 16 is 4, so 4 and a 4. Square root of h squared is h and an h. I know I'm going to have a plus and a minus. Then I have 9a squared, which is also a perfect square. Square root of 9 is 3, so I have a plus 3, minus 3. And then square root of a squared is a and a. So it factors into 4h plus 3a times the quantity 4h minus 3a. Okay, so you have a huddle. So I want you to pause the video, work on these two problems, and then when you're ready for the solution, unpause the video. So if you check out the first one, a 121 minus 4b squared, you notice a 121 is a square and negative 4b squared is also a square. So we have a difference of squares, so we can follow our pattern, get our 11 plus 2b, and then the 11 minus 2b. Now looking at the next one, it was a little different. We have a 27g cubed minus 3g. If you notice, both of these have a factor of 3g, so we can factor out a 3g here. It's a GCF, so we can factor it out. And that leaves us with a 9g squared minus 1. Now, if we notice 9g squared, that's an easy perfect square to see. 9 is a square, g squared is c. But this 1, that is also a square because 1 times 1 is 1, so it's a square. So we also have a perfect squares and 9g squared minus 1. So that'll be the square root of the first term, and then plus the square root of the second term, plus the square root, or minus the square root of the third term. So that one's just a little bit different. So we have another one to factor here. We're going to factor b squared minus 16. If you notice, I'm not b squared, I'm sorry, b to the power of 4. This b to the power of 4 is a square because the square root of b to the power of 4 is b squared. And also 16 is a perfect square, so we do have a difference of squares here. So this will factor into b squared minus 4 and b squared plus 4. Now, if we look at the question, can this be factored anymore? We're going to look at these and see if we have anything else that can be factored. If I check out b squared plus 4 here, well, that's not a difference of squares. There are no factors of positive 4 that will give me a 0 because they will both be positive, both be negative, so I can't get anything to cancel out. But if I look at b squared minus 4, that b squared is a perfect square, and the 4 is a perfect square. So we have another difference of squares. So can this be factored anymore? And that is yes. We can factor the b squared minus 4 into b plus 2 and b minus 2, and we're still left with a b squared plus 4. So that was an example where just doing this difference of squares once wasn't enough. We had to do it a couple times. So sometimes we need to use the difference of squares factoring technique more than once. Here's an example of that. If we look at 625 minus x to the power of 4. 625 minus x to the power of 4. If we take the square root of 625, we will get 25. So we know that is a perfect square, so we do have a difference of squares here. So this is going to be equal to 25 plus x squared, because the square root of x to the power of 4 is x squared, times 25 minus x squared. So we're looking at the first one. We can't do anything else with that. That's a sum of squares. We can't factor that. We look at 25 minus x squared. Well, if we remember, 25 is a square. X squared is a square, so we have another difference of squares. So this 25 plus x squared is coming along for a ride. And then we can factor 25 minus x squared as a difference of squares. So the square root of 25, so 5 plus x, and then a 5 minus x. And then that is all the way factored. So you have another huddle here. I want you to factor all of these completely. These are all examples where you're going to have to use the difference of squares technique all more than once. So go ahead, pause the video. When you're ready for the solutions, go ahead and unpause the video. So here are all the solutions to the huddle problems. The first one was y squared plus 1 times y plus 1 times y minus 1. The second one, we only had to do the difference of squares once. The square root of 4a squared is 2a squared, so we have a 2a squared here and a 2a squared there. But when we go to look at the second factor with the minus, the difference, we notice that 2 is not a perfect square. So I can't go any further with this, so that is my answer. Looking at the next one, 81 minus x to the power of 4, that will factor into 9 plus x squared times the quantity 3 minus x times the quantity 3 plus x. So that one is also done, no more difference of squares. And then the last one, 16 y to the fourth minus 1, will factor into 4y squared plus 1 times 4y squared minus 1. Looking at the second group, that is a difference of squares, so we can factor that. 4y squared plus 1 comes along the rod, and then it'll factor into 2y plus 1 times the quantity 2y minus 1. So we have one more problem to do, m squared minus 64, just a simple factoring. So I'll walk you guys through this one. M squared is a perfect square. Square root of 64 equals 8, so that is also a perfect square. So we got a couple perfect squares there. That means we can use the difference of squares technique. So I have two binomials, square root of the first term in the first spot, square root of the second term in the second spot, so an 8 and 8. And then we need a plus minus to take care of that negative. And then that is our solution. So there you go, guys. Quick lesson. Go ahead, get started on your homework. It is on Google Classroom, right where you found this video. So go ahead, get working on that. See you guys tomorrow. Have a great day.